In this PowerPoint, you are going to learn about the definition of a sequence, the difference between explicit and recursive sequences, and how to work with sequence notation. The set of notes is also available in PDF form on Canvas for you to download, print, or view as you choose. A sequence is a function whose domain is the set of positive integers. Sometimes we use 0 for certain application problems, but we're going to start with just using positive integers for these examples. So if I gave you a function but limited the domain to the set of positive integers, and you substituted 1, 2, 3, etc. into the function, you would generate a sequence. Here's an example. This is a sequence generated by putting x equals 1, 2, 3, 4, and 5 in the function below, f of x equals 3x minus 2. Notice when we put in 1, for x we would get 3 times 1 minus 2, giving us 1. 3 times 2 minus 2 is 6 minus 2, or 4. 3 times 3 minus 2 is 9 minus 2, which is 7, etc. So this is the sequence of numbers generated by this sequence rule. We can look at the sequence and see a pattern. This pattern is adding 3 between each number. Now for a sequence we usually use a little different notation than for functions. We use the letter A for a term in the sequence and subscript it with the term number. The term number is also the number that you substitute in the formula for a sequence to get that term's value. This is called an explicit formula. Here's what the formula looks like. A sub n is the term number. I'm going to back that up. A sub n is the term in the sequence in position n, and n is the term number. You can generate, for example, the fifth term in the sequence by substituting 5 for n. So this would be written a sub 5, the fifth term in the sequence, is 3 times 5 minus 2, which is 13. See, it matches the fifth term above. So let's use sequence notation to write the first 5 terms of this sequence. Notice what we're going to do is substitute 1 for n. A sub 1 equals 1 squared plus 1 equals 2. So the first term in the sequence is 2. Then we're going to do the same thing with 2, with 3, with 4, and with 5. So what do you think the sixth term is? 6 squared plus 1. Can you figure out the formula for this sequence? A good first step is to number the terms. Then try to determine a relationship between the term numbers and the terms. So we have 5 terms, 1, 2, 3, 4, 5. Notice that each term is twice as big as the term number, except that the terms also alternate signs. So our equation so far is a sub n equals 2n. If we multiply the term number n by 2, we would get 2, 4, 6, 8, and 10 for the first 5 terms. But what can we do to make the signs alternate? So far we have a sub n equals 2n, 2, 4, 6, 8, 10. To make alternating signs, I need a negative number raised to a power. Recall that if we raise a negative number to a power, if we raise a negative number to an even power, it is positive, and if we raise a negative number to an odd power, it is negative. That's why we need this negative 1 to the n, or negative 1 to the n minus 1. Let's substitute n equals 1, 2, 3 and see what we get. After I do that, you'll see why I have 2 different versions. In version number 1, when the term number is odd, we're raising negative 1 to an odd power, giving us a negative number. When the term number is even, we're raising negative 1 to an even number, giving us a positive term. Now when we use negative 1 to the n minus 1, we get the opposite effect. A An odd term number ends up giving us an even exponent and a positive term. An even term number ends up giving us an odd exponent and a negative term. So a sub n equals 2n to the 2n times negative 1 to the n gives us this sequence. And a sub n equals 2n times negative 1 to the n minus 1 gives us this sequence. When we do negative 1 to the n, the even terms are positive. When we do negative 1 to the n minus 1, the odd terms are positive. The second one is the sequence we wanted. So the second rule here is the explicit rule for the sequence 2, negative 4, 6, negative 8, 10. So far we have defined a sequence using an explicit rule. Each term is defined as a function of the term number n. Another way to define a sequence is using what we call a recursive rule. Basically, it is the rule of what you do to a term to get the term after it. We saw this pattern in the first sequence. Notice to get to the next term, we just add 3 to each of the previous terms. The recursive formula would look like this. The first term must be given because we have to have something to, we have to have a previous term to add 3 to. Then we write a sub n equals a sub n minus, or a sub n minus 1 plus 3. A sub n is the nth term. A sub n minus 1 is the n minus 1 term, or the term right before the nth term. Then we do plus 3. So let's write the recursive rule for this sequence. What do I do to get to the next term? Well, hopefully you notice that you multiply the previous term by negative 2. So I would write a sub n equals negative 2 times a sub n minus 1, a sub n minus 1 being the term prior to a sub n. But wait, don't forget, the recursive formula must include a starting point to refer back to. I must write a sub 1 equals 3, or I won't be able to apply this part of the rule to anything, because I need to know the previous term. So I use this rule starting with n equals 2, because I already know what a sub 1 is. What is the disadvantage of the recursive formula, though? If I wanted to find a sub 10, I would need to know a sub 9. And if I wanted to know a sub 9, then I would need to know a sub 8, a sub 7, a sub 6, etc. That's no fun. If I want to find a term way down the row, I have to keep generating terms. So the recursive rule is useful for generating the first few terms, but the explicit rule is better for finding a term way down the line, like the 100th term. Let's practice using a recursive form to generate a sequence. A sub 1, remember, tells us the first term, so we already know our starting point. A sub n is the rule then for finding all of the other terms, the second term, the third term, the fourth term, etc. This rule tells us to take the term number and subtract the previous term. So let's use this formula to find the second term. That, of course, is when n equals 2. So first of all, we write a sub 2, and we substitute 2 for n. We substitute 2 every place there's an n. So a sub 2 equals 2 minus a sub 2 minus 1, which is 2 minus a sub 1, which is 2 minus the term number minus the previous term. So 2 is the term number. The previous term is 1 because we know a sub 1 is 1. So 2 minus 1 is equal to 1. And that's our second term. The first term is 1. The second term is 1. Let's find the next 3 terms. Notice a sub 3 is 3, the term number, minus a sub 2. A sub 2 is 1, so we substitute the previous term 1 into our formula. a sub 4 is 4, the term number, minus a sub 3. A sub 3 is 2, so we have 4 minus 2, which is 2. So the third term and the fourth term are both 2. A sub 5 is 5 minus a sub 4, or 5 minus 2, since a sub 4 equals 2, and that gives us 3. So the first 5 terms are 1, 1, 2, 2, 3. It would be interesting to see if that pattern continues. This concludes the notes for recursive sequences and series, for recursive and explicit sequences and their notation.